Welcome back to ECE 320A. We'll start this lecture with just a few announcements. Homework number 1, I'm going to extend the deadline on that due date to the 31st. Stay tuned. Hopefully that will show up eventually, but we'll try to make that happen. But it will be the 31st, the due date for homework number 1. Homework number 2's due date won't change. That will be due a couple of days before the exam. Exam number 1 is scheduled for the 14th of February, and there is exam number 1 material on D2L for you to look at, study, prepare for exam number 1. What we want to do today is really just remind ourselves when we're in a sinusoidal steady state situation, all the transients have dissipated. If we're now playing with phasors, we have to treat those phasors as vectors, meaning we can't just work with magnitudes. We have to keep these vectors, components, clean, or at least keep them together, and we need to then consider these vectors as having a magnitude and a phase, or a real part and an imaginary part, and we have to consider both pieces of those phasors. We'll then quickly talk about maximum power transfer, and we'll try to start the conversation on power factor correction. What does that really mean? Well, that really means we're trying to introduce another subsystem, usually a capacitive type subsystem, that will move our power factor closer to 1. We know that a power factor of 1 is better, and once we get into that power factor correction and work through that problem, we'll see exactly why that is. But really, that can, by correcting the power factor, that can reduce the current demand that we are expecting from the power company. The power company may not have to produce as large a current if we can get our power factor closer to 1. And then that leads us into extending these ideas from single phase to 3-phase so that we can push larger amounts of power around. And now we have to think about or talk about 3 different phases instead of just the one single phase circuit. Again, we're thinking or we're working in sinusoidal steady state conditions, which means that all the transients have decayed and everything is oscillating at the same sinusoidal frequency. And what we can keep track of then are the voltages and currents in that sinusoidal condition, but we have to treat them vectorially. They each have a magnitude and an angle, or a real part and an imaginary part, and it's important that we keep track of all of those. And that's the same as what we've been doing with the complex power, is we're treating those as vectors. So it's nothing new, it's just now we have powers to deal with, which can be complex, and we also have voltages and currents, which combined appropriately create these complex powers, but the currents and voltages are also vector quantities. So here's an example just to get us thinking about this vector combination of voltages and currents, etc. Suppose we have this circuit. It's a series circuit, 2 loads. Impedance of load 1 is Z1. The impedance of load 2 is Z sub 2. This circuit is fairly simple. It's a series circuit, and we're supplying those with a voltage source that we're labeling as V sub G, and I've tried to bar these quantities to try to emphasize the fact that we are dealing with phasors. Here's the problem that we're given. Suppose that we know the magnitude of the voltage across the second load, and suppose that that has an RMS magnitude of 40 volts. We also know that Z sub 2 is absorbing 80 watts, and that load is in fact inductive. And so now, just visually, we can sort of see that, okay, we have the real power of 80, that's horizontal. We have a Q, maybe we don't know what it is, but it's going positive in the upward direction, and we know the voltage magnitude across that second load. Suppose we also know the following about the source. We know the magnitude of the source in RMS units, so we want to make sure that everything is consistent and we're dealing with maximum values or RMS values. Here we're using RMS values. Suppose that we're told that the magnitude of V sub G is 120 volts. We're also told that the real power supplied by the source is 100 watts, and you now should start seeing these pictures of complex power triangles, and we may have vectors and currents, voltages and currents that are represented as vectors. And we're also told that the net total load is inductive, meaning the combination of Z1 and Z2 overall looks inductive to the load, and we're told that the series current, this I sub S, has a magnitude. We're not told anything more than that, but has a magnitude, an RMS value of 5 amps. We don't know its angle. It's a phasor. Here's our problem. Given this information, can we find, or our task is to find the phasor voltage for load number 1. So we're given some magnitudes. We don't know the direction of those voltages. We know the magnitude of the current. We know that Z2 is inductive, and we know some powers of the second load and the source. This may not be given in a real-world problem, but you may just have to make an assumption. Here we're going to go ahead and assume that the current phasor is our reference phasor, so we're going to assume that the phase of our current is 0 degrees. Since nobody told us, oh, this is exactly the phase of this particular value, let's just pick one, and everything else now will be relative. All the other phasor values will be relative to that phase of our series current I sub S, and we're going to assume that is 0 degrees. So what are we given? Let's just remind ourselves and write down the data that we've been given for this problem. We know some information about load 2. Load 2, we know its magnitude, or the voltage magnitude, is 40 volts. And we know P sub 2 is 80 watts, and Z sub 2 is inductive. Now, if you get to going too fast, you might start mixing voltages and powers. Try not to do that. That's not what we want to do. We have a voltage magnitude of 40, and we have a real power of 80. Those are two different domains. We have complex power to deal with. We're not told what Q2 is. It's something, and we don't know, well, we do know something about the current through that because we have a series load. But let's continue. That's something that we kind of have to deduce from the given data. The other data that we were given was concerned with the source. And in this case, we were told that its voltage magnitude using RMS units was 120 volts. We were also told that the power of the source, so now I may confuse G and S, but we have a source. Maybe that's the generator. That's maybe where the G comes from on V sub G. But let's say the source power, real, was given as 100 watts. And we also know that the total impedance of our system was inductive. So now if we added up Z1 and Z2, we better have a positive j term, and we were also told that the magnitude of our current flowing through that series circuit was 5 amps. And what we're wanting to do is we want to now find V sub 1. And that would be easy if this was a DC circuit problem, because we're given VG, V2, and it's in a series circuit. We could find V1, but now we have to remember that these are phasor quantities, and it's not just working with magnitudes. So let's now look at finding that voltage phasor for V1. And the first thing that we assumed is we said, let's go ahead and let this current phasor be the reference phasor. And what that really just means is that I sub s, we're assigning it to have an angle of 0 degrees. We were told its magnitude was 5. We just didn't know where it was directed in terms of its direction. Now what do we do? Well, we can now just start applying some of our circuit analysis strategies, and in this one it's a series circuit. It's pretty maybe suggestive to try to write a KVL equation that will relate these voltages around this series circuit. And doing that, if we start at the lower left-hand corner, we can say, oh, we're going into the voltage source's negative terminal, so we'll have minus V sub G bar, and I've now just labeled these load voltages consistent with our passive sign convention for the current direction going from left to right. Now I have minus V sub G bar plus V1 bar plus V2 bar, and that should sum to 0. That's KVL. That will hold. It's just that now it's holding in a phasor form. So we have minus V sub G phasor plus V1 phasor plus V2 phasor equal to 0. And I hope you know that you can't just start taking magnitudes and adding and subtracting those. That's not what we can do. But we can now solve this for V1. That's what we're trying to find. And that's now V sub G minus V sub 2. From our given data, we actually have the magnitudes of V sub 2, and we have the magnitude of our source voltage, V sub G, but we also have the magnitude of our current. And the current is the same. It's in all of these elements, our source voltage and the two loads. We have the magnitude of the current flowing through load 2. We have the magnitude of the voltage. That actually then says that we have the apparent power of load 2. And if that's not coming to you, remember what we have. We have the complex power is V sub 2 of any element. It's S is equal to V I star. So we can now say that we know that condition is true. That's our complex power expression. But now we can take the absolute value or the magnitude of both sides and realize that the magnitude of a product is the same as the product of the magnitudes, which now allows us to say that S sub 2 magnitude is equal to V sub 2 I sub 2, but it's also I sub S conjugate's magnitude, but that's the same as V sub 2 magnitude times, and the conjugate has the same magnitude as the unconjugated complex value. So now we have the apparent power. That's what this is. This is now the apparent power of load 2. We now know that. So we have the apparent power, the magnitude of S2. We just don't know the direction yet. But let's start thinking through this. We can recall that the real power, we were given that, weren't we, is the apparent power times the power factor, or the cosine of the angle of that particular load. So in terms of load 2, we know that P sub 2 is equal to the apparent power of load 2 times the power factor of load 2. And we know it's inductive, and we can now, it might be easier or more intuitive to start drawing a picture so that we see what's going on. Here's P sub 2. We don't know this Q sub 2, but we do know that it's up, and we know this hypotenuse value, S sub 2. But in general, we can just say that that's S2, where that's at some direction, theta sub 2. So now from this power factor expression, or from this real power expression, we can solve for the power factor of load 2. The power factor of load 2 is P sub 2 divided by the apparent power of load 2. And we were given the real power, that was 80, and we can compute the apparent power, that was the magnitude of the voltage times the magnitude of the current of load 2. This is nice. So now we have that our power factor of load 2 is 2/5, or 0.4. With a power factor of load 2 equaling to 0.4, and we know that it's lagging, we also know that the power factor of load 2 can be used to find the angle, because we know that the power factor of load 2 is going to be the inverse cosine. We know that the power factor of load 2 is the cosine of theta sub 2. And now we can simply solve that for theta sub 2. So now we know that theta sub 2 is equal to the inverse cosine of power factor of 2. And since it's lagging, that tells us the sign, that it's a positive angle. We now have the inverse cosine of 0.4, and that now gives us a plus 66.4 degrees. That's theta sub 2's angle, and theta sub 2, remember, is theta V2 minus theta I2, and we know that theta sub I2 was 0. Since I sub S as a phasor was 5 at 0 degrees, this angle was our theta sub I2. That says then that the angle of V sub 2 is actually going to be theta sub 2, which is 66.4 degrees. Since theta sub I2 we assumed was our reference, and that was 0. So now we have this phasor form for the voltage across load 2. That's now 40 at an angle of 66.4 degrees. And this theta sub 2, as we just said above, that's theta sub V minus theta sub I. That's 66.4 degrees minus 0 degrees equals 66.4 degrees. But theta sub 2 is our angle. That's the difference between the voltage phasors angle and the current phasors angle. Well, that's just the angle of our impedance. So this is now the angle of load 2's impedance. Now, we have one phasor found. We need to find some more. We were given information on the source, and we also know this KVL equation has to be true. So if we could find the source power or the voltage associated with the source, then the phasor quantity, then we could find V1. So let's now see if we can find that by playing with some of the formulas associated with the source power. We know the source power, complex power formula, is now V sub G I sub S star. But that's just the magnitude of V sub G at an angle of theta V sub G, and it's the magnitude of I sub S at an angle of minus theta I sub S. So that this is now V sub G magnitude, I sub S magnitude, angle of theta sub V sub G minus theta sub I sub S. This phasor notation can actually be written as a complex exponential. This is really just e to the j theta V sub G minus theta I sub S. And we can now use Euler to break that into its rectangular components so that we now have a real part associated with our source complex power. The complex power is now the magnitude of V sub G times the magnitude of I sub S, and now let's go ahead and apply or use Euler to rewrite e to the jx as cosine x plus j sine x. We now have cosine theta sub V sub G minus theta sub I sub S minus, where'd the minus come from? Shouldn't have, plus j sine theta V sub G minus theta I sub S. Distributing that apparent power through both terms, we now have V sub G I sub S cosine theta V sub G minus theta I sub S plus V sub G I sub S sine theta V sub G minus theta I sub S. This is just the real power of our source. And what did I forget? There's the plus j. Hopefully I kept that in. And this, I guess I could use the colors that we've been traditionally using, is the reactive component of our complex power of our source. So here is now our source complex power, so that now we have S sub S is P sub S plus J Q sub S. We were given P sub S. P sub S was 100 watts. We were given V sub S, magnitude of 120, and we were given the magnitude of, I told you I would probably change that around. V sub G was 120. I sub S was 5. Now can we use that to our advantage based on what we know? Well, we know that P sub s, formula-wise, is the apparent power, which is the product of voltage magnitude times current magnitude cosine theta V sub g minus theta I sub s. And this is the power factor of our S. We know what this angle is. This was 0 degrees. That we assumed was our reference. And now we know the left-hand side. That was 100. We know V sub g, we know I. The only thing we don't know is this power factor, and we actually know a little bit about the argument of that power factor because we know that theta sub I sub s is 0 degrees. So now we can say, oh, the cosine of theta sub V sub g minus theta sub I sub s is actually equal to P sub s over V sub g's magnitude times I sub s's magnitude. And this we were told was 100. V sub g was 120. And I sub s was 5. So now we know, and this is the power factor of our source. This we know is 0 degrees. The power factor of our source is now 20 over 120, or canceling a few things and dividing things out, we now see that the power factor of our source is 1/6, and we can find the angle of our source based on that power factor. Theta V sub g is now equal to the inverse cosine of 1/6. And we knew that everything was inductive, so this is going to be a positive angle, and this is now 80.4 degrees if we take the inverse cosine of 1/6. Now we have the phasor form of our generator or source. We have the phasor form of load 2. Now we can go back and use our KVL expression to work with these voltage phasors and actually solve for what we want, which was the voltage of V sub 1. Remember, we had minus V sub g plus V1 plus V sub 2 equaling 0 from KVL, and that gave us then that V1 is, in fact, V sub g minus V sub 2, and V sub 1 now is a phasor. That's some magnitude at some angle. Whoops. And we can now solve for that, since we know V sub g as a phasor and V sub 2. So this is now going to be 120 at an angle of 80.4 degrees minus 40 at an angle of 66.4 degrees. Depending on how your calculator is set up, it might just go ahead and compute this. If you're doing it in more steps, you might have to now convert these polar forms into rectangular form, add their real components and imaginary components, and then put them back into a polar form. If we do that, this is now 120 times the cosine of 80.4 degrees plus j 120 sine of 80.4 degrees minus V sub 2, which is now 40 cosine of 66.4 degrees plus j 40 sine 66.4 degrees. Doing the algebra, then, we end up with V sub 1 will in fact be 4, not much real component, plus j 81.7. If we now put that's now some triangle with a real component of 4 and a vertical component of 81.7. We can find the hypotenuse of that right triangle. That now says that the hypotenuse is 81.8 units long, and its angle is going to be close to 90 since we don't have much real part, but we have a big imaginary part at an angle of 87.2 degrees. And that is now our voltage in RMS, where this is now our magnitude of V1 at an angle of theta V1. And what I would like for you to just realize, although it's fairly close because we don't have much difference in these angles, but note that the magnitude of V1, which is 81.8, is not quite equal to the magnitude of V sub g, which was 120, minus the magnitude of V sub 2, which was 40. So that's not equal to 120 minus 40 equal 80. It's pretty close in this particular example, but it's not the same. That's not a numerical rounding error. And you can see that in a picture. Suppose we draw V1. That's 81.8 or 82 at an angle almost 90 degrees, 87.2. So let's now say that we are going to draw V1. It's 82 in length, and let me say here's my, so there's now V1, and we add to that V sub 2 from KVL. This we could write as V sub g is equal to V1 plus V2 if we wanted to, and that's what we're doing now. So now let's add V2 to that, and V2 was this length of 40 at an angle of 66.4. Let me use a different color for that. So now V sub 2 is going off like this at a half the length essentially of V sub 1, and that combination is our V sub g. And you can see that that triangle is not that, doesn't have that much area inside it, and that's why V1 plus V2 is almost equal to V sub g in this case, but it's not quite. Where here, this angle was our angle of V sub g. That was 80.4 degrees. The angle of V1, which was a little bit larger, that was 87.2 degrees, and then the 66 degrees of V sub 2, these angles are always measured with respect to this horizontal real axis. So this particular angle right there is the angle of V sub 2, which was 66.4 degrees. And the lengths were what they were. V sub g was 120 degree, or 120 at an angle of 80.4 degrees. V1 had a length of 82, and V2 had a length of 40. So it's almost there, and that's because this triangle really isn't very big. And so V1 is almost, V1 plus V2 is almost V sub g. And if you draw that a little bit more accurately, you would see that in fact we can't just add the magnitudes and be done with it. That's what's happening with voltage phasors. The same can be said for currents. In sinusoidal steady state conditions, that gives rise to magnitudes and angles, so that now these phasors for currents also add vectorially. Meaning, let's just look at a simple example. Suppose we have a current source, I sub s, in sinusoidal steady state, and it's feeding a couple of different loads. We have a Z1 and a Z sub 2. Then if that's the case, we have I1 and I sub 2 by a voltage divider relationship, and we could write a KCL equation at this node, and KCL now says that I sub s is equal to I1 plus I2. And if you wanted to, I'll let you do this at home, but as an example, maybe illustrating this a little bit more dramatically than the voltage phasor example did just a minute ago, but suppose we had I sub s equal to 10, I sub 1, that 10 could be made up many different ways. Suppose that it's made up of I1 being 7.13 at minus 52.48 degrees, and I sub 2 is equal to 8 at 45 degrees. And I hope you can see that 10 is not equal to 15.13. But vectorially, you can see that, in fact, this is true, that I sub s is equal to I1 plus I2, where if we did it, let me see if I can draw this a little bit. Here is, let's say, I1. That's now a length of 7 at an angle of minus 52.48. Then we have a length of 8 for I sub 2 at an angle of 45 degrees. And adding those head to tail gives us I sub s as a purely real current with no angle. That's of length 10. And there's the graphical justification for that example. Keep in mind then that phasors have to be added vectorially. That's illustrated right here in this graphic of KCL. Let's now move into the next topic, which is maximum power transfer, and we're doing this under sinusoidal steady state conditions. You've probably, I hope, seen maximum power transfer before, and maybe you've done it or used it for purely resistive circuits. Now maximum power transfer is really similar. It's just now we want to match the source impedance with the load impedance by, in fact, making those complex conjugates of one another. So we're matching the load impedance. If we had the ability to select that load impedance relative to the source, we're matching the load impedance with the source impedance. And matching is not meaning setting equal to quite. It's actually meaning that the load impedance, C sub L, is the complex conjugate of the source, or the Thevenin impedance. And I should say we probably don't want to be doing this in a power situation, meaning if we're pushing large amounts of power. This matching of load impedance in sinusoidal steady state is useful if we're dealing with sensors or communications. Then we want to match our loads, match being with these conjugates, so useful for communications and sensing environments. As I said, it is not really what we want to do in a large power setting. It is not really what you are looking for in moving large blocks of power. And we'll move much larger blocks of power in the next chapter when we get into three-phase circuits. And the reason why it's not a nice thing to do in a real power scenario is because with this matching scenario, you're actually losing the same amount of power in the source as you are at the load. And you really don't want to put half of your power consumption at the load or at the source side. I'm sorry, either one. You want to put most of your power, you want to distribute that out to the load, so you do not want half of your power consumed on the source side of the terminals. And I will just refer you to the text for that detail-wise. For more details, see section 10.6 in the textbook. Where the diagram, let me just remind us of what we're dealing with here. The diagram is really saying here is our Thevenin equivalent, let's say between terminals A and B. Here's our Thevenin impedance, here's our Thevenin voltage as a phasor. Then if we have the ability to design the load such that we distribute maximum power to that load, then Z sub L is actually going to be selected to be the conjugate of the Thevenin equivalent impedance. Now it actually might be a good time to sort of caution you when you're dealing with power and you're trying to maybe analyze a circuit and you want to maybe do some Thevenin equivalence in the analysis. Well, back off a little bit because there is a caution. The power conditions, or Thevenin, I should say, Thevenin equivalents, really are only useful for creating similar electrical conditions, currents and voltages at the terminals. It's not telling us anything about being equivalent relative to the power consumed by either the Thevenin equivalent circuit or the Norton equivalent. So there's caution when using Thevenin equivalence in power problems. And maybe one way to drive that point home is to say, okay, here is V Thevenin and here is Z Thevenin, the Thevenin equivalent. And what is its Norton equivalent? We want the same behavior at the terminals. And let's just say I sub n. And what is I sub n? Well, this voltage across AB needs to be the same as what it is across AB here, so that needs to be V Thevenin, so that we now have V Thevenin is equal to Z Thevenin I sub n. But what I'm cautioning you to be aware of is the fact that you can't be replacing circuit elements with its Thevenin equivalent and hope to achieve the same power supplied by a particular source. Meaning, what's the power supplied by V Thevenin here? What's the current flowing through that voltage source? There is none because it's open circuited. So here the power of the source is 0. What about over here? The power supplied by I sub n, now that is feeding Z Thevenin. And we know that that can be used to give us P of the source is now Z. Well, it could be complex. So what do I want to, well, we just said, it's okay. Let's just say the complex power here is what? Z Thevenin I Norton squared. And I Norton is non-zero, so we do have something that's not equal to 0, and you can see here is the disconnect. We can't be, if somebody says, oh, what's the power delivered or supplied by the source, you can't now replace circuit elements with their Thevenin or Norton equivalent and expect those equivalent circuits to produce the same kind of power behavior. So please note that there's a big caution when using Thevenin equivalent in power problems. You can use those to find maybe what's happening beyond the terminals in terms of power consumption, but don't go back so far or to the left as I've sketched them here and trying to say anything much about the power supplied or delivered by the source. I hope that helps if you are now trying to analyze a circuit and finding that, wait a minute, my analysis isn't consistent because what this source is not giving me the same power as the equivalent source. So just be cautious. One more topic in single-phase circuits that we want to work through before we move into Chapter 11 is power factor correction. And what do we mean by that? Suppose now that we have two loads. Load 1, let's say P1 is now 48 kilowatts with a power factor of 0.6, and suppose we're told that that's lagging. We can't just say a power factor of 0.6 and know everything we need to know about that load. Suppose load 2 has a real power, P sub 2, of 24 kilowatts, and a power factor of this load is 0.96, closer to 1, which is a good thing. And suppose now somebody says, oh, that's a leading power factor. Lagging, we have an inductive load. Leading, we have a capacitive load. Suppose these are both serviced or supplied by one source, and that source, let's say, is a voltage source of 500 volts RMS. And in these power factor corrections, a lot of times we do need to know more information depending on what's asked. So let's just assume that if we need it, the frequency that we're dealing with in a sinusoidal steady state is 60 hertz. And here is the current that's being demanded of our generator to supply those two loads. So now if you're sitting here and you're operating two loads and the power company is feeding you with V sub G, we want to know, is there a more effective way, or a more efficient way to demand power from the supplier or the power company, so that we know that I sub G is I1 and I2 in phasor form. What we want to do now is, in fact, reduce our bill or make the power company's job easier. And the way that we will do that, I think you can see that net, and we'll work through this, but net, this looks like a more inductive load than capacitive, because we have a real power of 48 and we have a leading power and a real power of 24. If we now have a net inductive load, maybe we can reduce that power factor of that combination by introducing another load near the load, away from the source, that looks more capacitive, so that maybe we could even find a capacitor which has an impedance of 1 over j omega c. There's where the frequency comes into play. Maybe we could pick the capacitor C such that the combination of this added capacitor, load 1 and load 2, actually has a complex power, or has a power factor of 1. Is that possible? That's what we want to look at in terms of power factor correction. Maybe we will find that with just load 1 and load 2, our power factor is, let's just throw a number out there, it's maybe not the same here, or if I go ahead in my notes, maybe I can find that. Maybe it's close to 0.8. Well, maybe that's a little bit too low, and we would like that to be closer to 1. Can we make it equal 1 by the appropriate choice of this capacitor C that we're now introducing, again, near the load, so that maybe, and what we will see is that without that additional capacitor, the magnitude of this source current, I sub G, is much larger than if we correct the power factor with the appropriate choice of C to drive our power factor closer to 1. So to get us working this problem, we actually need to obtain some intermediate information, and one is actually to go ahead and try to find the complex powers associated with load 1 and load 2. We need to know more than just the real powers. If we're going to try to change the reactive power seen by the source at load 1, load 2, and an additional capacitor, we're going to need to know what those reactive components are. So here's a quiz. Can we now find, with the given information, the complex power S1? That's the complex power of load 1. And if you were running late on your exam or you had just a few minutes left, what would you do? Well, you could at least get half of S1. Maybe you wouldn't get half of the points, but you know the real component. You know that that's 48. Now what you need is to fill in what is Q. That's what we don't know. But we also know the power factor, and we know it's lagging, so we could start to see some of this complex power developing quite quickly in terms of a solution. We now have P1 of 48K. We want to find what is Q1, and that will then take us to finding this length of S1 and this angle of load 1's impedance, theta 1. What do we know? Well, we know that the power is equal to the apparent power cosine of theta, where this is now our power factor. We can now solve for S1 in this particular example, the apparent power of load 1. We know the power factor and we know P. So we know P1 and we know power factor of 1. So now we can find the apparent power of load 1. This is 48K divided by 0.6, and that ends up being 80 kVA. So this hypotenuse is now 80K. And if we wanted to, we could find the angle, but we could also now, if we have a right triangle and we know the horizontal side and we know the hypotenuse, we can now find by Pythagoras a squared plus b squared equals c squared. We now know that S1, the magnitude, is the square root of P1 squared plus Q1 squared. Or we can now solve that for Q1. Q1 is now the square root of S1 squared minus P1 squared. A lot of different ways to solve this. So plugging in the numbers, we find that Q, and it's lagging, so we know that it's up or positive. It's now 64 kilovars. So S1 complex power is now 48 plus J 64 kilovars. That wasn't so bad, and it didn't take us too long to deduce that. What about complex power for load 2? Well, we're given the same information in terms of variables. They're just different values, and this one's now leading, so now we know our Q is going to be negative, but we can find S sub 2. We can find the apparent power for S sub 2. That's now the given real power divided by the power factor, and we can get the sign of that Q eventually because we know it's leading. But this was now 24K divided by 0.96, so that's not going to change much. It's actually 25 kVA in terms of its magnitude. Q2 is now the same side argument, Pythagoras. We now have this is going to be the magnitude of S2 squared minus P sub 2 squared. That will give us a positive number, or we could say, oh, this is plus or minus the square root, and what we want to do is actually take the minus, because we know Q sub 2 was giving rise to a leading reactive component. So that sign of minus is because we were told our power factor was leading. So that now we have S sub 2 is 24 minus J7 kVA. Now what? Well, now we actually have a lot of useful information. We now can find the total complex power associated with just loads 1 and load 2. It doesn't matter about how they're interconnected. In this case, they're connected in parallel. They could have been connected in series. We can find their total complex power by simply adding the complex powers of load 1 and load 2. The total complex power now is, let me call it S12, is going to be S1 plus S2, and I might say that that's P12 plus JQ12, where the P's and the Q's I can find. I know that P12 is just the power, real powers from load 1 and 2. I can add these component-wise. That's now 72 kilowatts. Q12 is now Q1 plus Q sub 2. Remember, Q1 was positive, Q2 was negative. We're algebraically combining these. Q2 was minus 7, Q1 was 64. So we have 64 minus 7, or that should be 57 kilovars. Now we know what S12 is. S12 is now 72 plus J 57 kVA. And we could write that in polar form by finding the magnitude of that and its angle. Doing the calculations, hopefully I have, or maybe your calculator can convert rectangular to polar. We now have a parent power of loads 1 and 2 of 91.8 kVA at an angle of 38.37 degrees. That's S12. And what do we want to do? We actually would like to make that angle by the introduction of this capacitor. Now we want to add in essentially a third load due to this capacitor, and we want now the combination of load 1, load 2, and load 3 to actually produce a zero angle, so that we now have a power factor of 1. So our goal, now that we have the total complex power associated with loads 1 and 2, our goal is to find, and that angle is positive, so it is inductive. We want to find a capacitor to actually drive the power factor of load 1 plus load 2 plus the capacitive load. Find a capacitor to drive the power factor of load 1 plus load 2 plus capacitive load, let me say, close or equal to 1. That's what we want. And next time we will look at what that means relative to the current requested from our source voltage. you can now find I sub g. Now that you have S12, you could find what is required. So now we could go back and we could say, oh, S12 is V sub g I, let me get the, did I call it I sub g or did I call it I sub s? I'm sorry for scrolling back and forth. I sub g. We know that, and we know V sub g. We could set V sub g if we wanted to a particular, as our reference, or we know the apparent power. We know the apparent power of S12 is now the voltage V sub g, or the magnitude of V sub g, and the magnitude of I sub g. The magnitude of I sub g is now simply the apparent power divided by V sub g. The apparent power we just calculated, and we calculated it in the above analysis when we were just looking for the complex power of loads 1 and 2 in polar form. That's 91.8, and our original source voltage was 500 volts, but this is now K. And if we do that division, hopefully we will find, I'm not sure that I've actually done that, but this now ends up being I sub g in terms of the magnitude of the current that we're requiring the power company to provide us with loads 1 and 2. That's now 184 amps. Is it possible by introducing a capacitor here, is it possible by introducing that additional capacitor that we can actually drive this current magnitude to be a number smaller than 184 amps? That would be ideal, and the way that we're going to achieve that is by improving our power factor. That's our power factor correction, and that will now be what we pick up with or start with next time.